Hey everybody, alright, we're continuing our discussion of Chapter 13, which is alkynes, kind of the synthesis of alkynes, the reactions of alkynes, and the reactivity of alkynes, all those kind of things. A couple of the key things we learned about last time, I'm not going to review it all, but one of them, of course, was that you could take an alkyne, it's all from last time, and like rip off the proton because it's somewhat acidic, so butyl lithium or NaNH2. Rip off the proton, abstract the proton, and then have it attack something like an electrophile. Like what are the electrophiles? It could be a ketone, aldehyde, or epoxide. In this case, it attacks the epoxide, opens up the epoxide, and the hydroxy group is there on the right, separated an atom from the squiggly line, right? So that was kind of like one of the things we talked about last time. And the other thing, of course, that we kind of ended on was that there's kind of three ways you can reduce alkynes down to alkane, well, alkanes and alkenes. One of them, well, the three ways are, of course, H2 palladium on carbon, which reduces them completely down to alkanes, and then we have like the H2 Lindlar method, which makes cis alkenes, so the H2 gets delivered in a syn addition, which makes a cis product, so you get like carbon, alkene, carbon, H2 Lindlar, and also either sodium or like lithium and ammonia, and that does a trans reduction. So then the mechanisms, of course, were very, very different. These mechanisms are very similar. The difference is Lindlar stops halfway, whereas this is like a two reductions. First it reduces from alkyne to alkene, and then it goes from alkene to alkane, and you get the fully saturated group. Okay, and then, yeah, this, for whatever reason, this catalyst mixture stops halfway, and it only adds an H, two H's, but in a kind of cis fashion. And this was that kind of crazy radical mechanism that we saw. Alright, so continuing, and this kind of puts together a couple of the reactions we just saw. Let's think about a short synthesis type problem. Synthesis. Type of thing you might see on a quiz or something. So let's just assume we got a benzene with an alkene, and we were going to do a couple step synthesis to make basically the same thing, but with a cis alkene and a methyl and an alcohol. So this is not some simple problem where we just magically attach this thing, right? It's going to be a couple steps, and this is going to use some of the new reactions we've learned, right? Okay, so usually when I begin a synthesis, and remember, synthesis does not mean mechanisms, so we're not going to do the mechanism of any of these reactions. We don't really need to draw the arrows. We're just trying to make a string of reactions that gets us from the starting material to the product, right? So I usually think strategically. I'm like, what are some of the reactions I'm going to be needing? So I'll write like strategy, question mark. So what are some of the reactions I might need? And maybe electrophiles, any kind of things that might help me when I actually step through this, right? First thing is, I'm starting with an alkene, right? And alkenes don't do any of this. And if you remember that, we didn't have a way of, like, turning a terminal carbon of an alkene into a nucleophile, like to attach this, right? That's not a thing we know how to do. So obviously this piece is being added, but it's not like I can just do that with the alkene, because we never learned of doing that with an alkene. But we do, what chapter are we in right now? We're in alkynes. So assuming you made this into an alkyne somehow, then you would have access to alkyne chemistry, right? So yes, there's an alkyne, probably, and maybe we can convert the alkene to an alkyne, and you know how to do that too, those last chapter, or last section. The other thing is, I see a cis alkene, right? Cis, it's like a benzene, it's an alkene that's cis. And what is our method of making cis alkenes from this chapter that we learned just like, briefly ago? It was that whole H2 Lindlar thing, right? So if we have an alkyne, we can convert the alkyne into a cis alkene using H2 Lindlar. So in my little strategy section, I'm just going to write H2 Lindlar. Of course, that's another thing we'll probably use. We're not sure the exact order, but yeah, we definitely got to use alkynes, maybe H2 Lindlar. The other thing is, like, when we eventually attack this piece as an electrophile, are we going to attack a ketone, aldehyde, epoxide, or some other functional group to make this? And the answer is, you look at the squiggly line and you see it one atom away from the hydroxy group, and you say, is it ketone, aldehyde, or epoxide? Of course, when the squiggly is one away, it is going to be an epoxide. So some kind of epoxide, and we can actually make a guess what the epoxide is going to look like. It's going to be a 3-carbon epoxide. 3 carbons, and the epoxide would be right there, right? A 3-carbon epoxide. I'll just draw it. That's going to be the 3-carbon epoxide we use. Okay. All right. So we can, when we do synthesis, we can go in the forward direction. We can go in the backward direction. And in organic 1, we've talked about both of these. We're trying to emphasize going backwards. You could probably go forwards and get to the right answer, but I don't know. We're really, trying to emphasize retrosynthesis, going backwards. In the real world, or we'll say on a quiz, as long as you get to the right answer, it doesn't matter what you use. But you can go down the wrong pathway. If you go in the forward direction, you can get stuck, and then you just get a total nonsense answer. Usually going backwards, you'll get back to where we started, because you know where we're trying to get to going backwards. So anyway, what's the last step? What do you think the last step of the synthesis is? We know there's kind of 3 things that happen overall. We need to convert the alkene to an alkyne, and we need to do an H2 Lindlar, and we have to do the epoxide reaction. It kind of makes sense, because when we do the epoxide chemistry, we need to have an alkyne, and right now we don't have an alkyne, we have an alkene. So maybe what we should do is have the last step be H2 Lindlar. So from the alkyne to the alkene, H2 Lindlar, right? Now we just have to draw the corresponding alkyne. Remember, when you draw an alkyne, you can't draw it bent to like an alkene, so you have to kind of redraw it a bit. Okay, so now these 2 carbons are these 2 carbons, and then we have a CH2, CH, and a CH3. So 3 carbons. 1, 2, 3. 1, 2, 3. Yeah. Where's the hydroxy group? On the middle one. Still draw my squiggly right there. Of course, that's that's the CC bond we're going to form, because we assume we start with 2 carbons, and those are the 2 carbons, But anyway, so maybe now we're ready to attach that piece, because we have an alkyne. We can attach things to an alkyne, like an epoxide, right? This is where you think carefully and maybe use your thumb or something to kind of cover parts of the molecule up. You're like, who's going to be the nucleophile, who's going to be the electrophile? I think alkynes are good nucleophiles, so maybe that's going to be my nucleophile. And what's my electrophile? Well, those are the atoms, right? But of course, that won't be the electrophile itself. It'll be the epoxide, because the epoxide is the thing that if we attack the epoxide, it opens up and gives us the alcohol, right? So anyway, now I can basically, I'm going to draw the nucleophilic alkyne. Okay, and of course, if you look at our last lecture, it's a three-step process. We need a strong base, we need an electrophile, and then we need like a water or something. So 1, 2, 3. 3 is always the easiest, water. And then pick our base. It can be N-butyl lithium, or it could be sodium NaNH2, sodium amide I think it's called. I'll do butyl lithium this time. Okay, and what's our electrophile, the thing we're going to attack to build this molecule? And we did that when we talked about strategy. It was the epoxide, right? So a little congested there, but it's 3 carbons, right? Carbon, 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 right? See that? It's a 3 carbon epoxide. Carbon, carbon, carbon is drawn nicely up there also. Okay? Alright, so we're still not done. Of course, how do you go from an alkene to an alkyne? Well, that is, we learned that first thing in this chapter. It's a 2-step process. Remember that? It's the double elimination. First you dibrominate an alkene, and then you double eliminate it with a base. So if I go backwards, it's going to be, this is where you need to know your reactions. And I like to say, you got to know them forward, you got to know them backwards. You got to know the reactions in and out, and index cards are a way to do that. Even if the course is open note, it doesn't give you an excuse to just kind of, not study. You have to know these reactions, right? And of course, the first thing we learned with alkynes is that you can essentially first do a bromination of the alkene, so that's Br2. And then once you got the dibromide, you can double eliminate. So you rip off one proton to make an alkene, rip off the other proton to make an alkyne, and you just use NaNH2 there. Remember, the other thing is that base is sometimes used as step 1 for this reaction as well. So this is kind of a versatile base. NaNH2 can be used for the double elimination. It can also be used for the deprotonation of the alkyne. Alright? Cool. So that was a fun synthesis problem. Alright, so now we're on to number 7, which was addition reactions to alkynes. Addition reactions to alkynes. Addition reactions to alkynes, and we're going to first introduce this stuff by kind of talking about what you already know from alkenes. So let's recall some alkene chemistry real quick. Recall that alkenes, which was chapter 12 in the book, attack electrophiles. So a lot of the end of Organic 1 was kind of how alkenes attack electrophiles, right? So we're going to review some of these reactions, but we're going to do it kind of quickly, and I'm not going to really go through the mechanisms very intensely. We need to know mechanisms for alkynes, and by reviewing the alkene reactions it helps, but I don't have time to go through every one of the alkene reactions in super detail. So let's just, I'll say mechanisms are abbreviated. Mechanisms are abbreviated. And you can fill in the details to review the alkene reactions. You fill in details. So I'll show maybe the key intermediates, the mechanistic intermediates. So let's think about like this reaction. This is an alkene, and we react with HBr, right? Alkene, HBr. Is this Markovnikov or anti-Markovnikov? Think about your old chapter 12 stuff. And of course, what's added? Well, an H and a Br, right? So one atom gets an H, the other atom gets a Br. This is Markovnikov. I'll just say Markovnikov. Of course it's Markovnikov. So the Br goes to the more substituted of these carbons. So the left carbon, right? Of course the H goes to the right carbon, okay? Thinking mechanistically, how did this work in a nutshell? And I will draw a little bit of the mechanism just for your review, but yeah, the alkene attacks, right? That's what we mean by the alkene attacks an electrophile. Well, the HBr is an electrophile. Alkene attacks it, and then you get a carbocation. Remember this? Remember carbocations? Of course, there's our H. And then Br minus can attack that. Br minus can attack that. What's pH? pH is a benzene, right? So if I wanted to draw this, I would just draw a benzene hanging off, at this position. So it'd be benzene and then 3 carbons. All right. So yeah, that was one of the one of the first examples from chapter 12, Markovnikov Hydrobromination of an alkene, right? Okay. What about what does this reaction do? What does this reaction do? Well, you probably make a guess, and you shouldn't have to guess because you should know this, but one atom gets a Br and the other atom gets a Br, so it's like product is BR-BR. Dibromination, right? Dibromination. Now, for the mechanism of this one, what's the intermediate look like? And the basic mechanism, the alkene attacks. And what's the intermediate look like? I guess. And is there a name for it? Okay, it's 3 carbons. We didn't change the carbon count. And now, when the alkene attacks, it's a little different than up here, which is just like it protonates and then you have a free carbocation. It's a little different than that. The idea is that a Br just kind of bridges the 2 atoms. And you have a plus charge, and there's a name. It's called a bromonium ion. A bromonium ion. And this kind of acts like, because there's like secondary position and a primary position, right? And this kind of has a secondary position and a primary position. This has secondary carbocation character, so it's a little more carbocation character on the secondary position, and that's kind of where the next step, where the nucleophile attacks, is kind of on the secondary position. So this just gets opened up like a epoxide or something. So, but my point is that this has secondary carbocation character. Secondary carbocation character, and so the Br minus, attacks on the other internal position, kind of like that, and opens up, and you get the product that way. Okay. All right. So then, well, keeping going on our little mini review of alkene chemistry. Another one, of course, if you have an alkene, do you remember the reaction that gives you a Markovnikov alcohol? So this is a Markovnikov alcohol. And of course, just for reference, this is not like Markovnikov or anti-Markovnikov. This is neither, because you get BRs on both positions. This is Markovnikov to make the bromide. This is Markovnikov also. So the question is what the reagent is, and a little bit on the mechanism. So anybody know? Think about it. is it a metal, maybe a funny metal? And it is. And this is the reaction I call OMDM, which is Oxymercuration Demurkuration. So it's a mercury-based reaction. And the mechanism and the reagents is it's Hg, it's O is acetate too. So it's like a Hg, and then you have two of these things on there. Those are acetate groups. And then you also need water for step 1. Okay? And then step 2 is NaBH4, sodium borohydride. Okay? And that makes a Markovnikov alcohol. Another abbreviation for this mercury thing is, I'll just draw it over here, is HgOAC2. It's the same thing. Acetate is, that's what an acetate group is. HgOAC2. Yeah. Okay. And what is the mechanism of this reaction? So it's kind of related to the bromonium one. So the alkene kind of attacks the mercury, kicks off an acetate, and you get 3 carbons, right? But now, instead of making a bromonium, it makes something with a mercury, OAC, right? And the bromine was positively charged. Who's positively charged now? The mercury. And this was called a bromonium. What's this called? A mercuronium. Mercuronium ion. And this had a secondary carbocation character. So the bromine would kind of attack the secondary position and open up. This one, is it primary carbocation character or secondary? Well, it's the same. These are very analogous. So this also has secondary carbocation character. Secondary CC plus character. Secondary carbocation character. So the water is a nucleophile. Remember water? How we have water right there. So where's the water going to attack? If we have secondary carbocation character, the water can attack the secondary site or the primary site. Who's it going to attack? You know, if it's electrophilic on the secondary, well then this is going to attack on the secondary, right? And it kind of opens up. And I'm not going to go through the whole mechanism, but this is just the key of, like, you know, how we get Markovnikov regiochemistry is what it's called. Okay, so HgOAC, OH2 plus, there's still a plus charge, right? There were a couple more steps that we didn't really explain, except that the loss of the proton's easy, right? Somebody just takes the proton off. But the hard step is, like, where does the mercury go, right? And that is the NaBH4 step, and this is something I traditionally use called magic, because, well, it's not really magic, and I actually have a great explanation for it, but it's not one of those things that I really want to get into unless you ask me. If you want to know what the magic is, I'll tell you what the magic is. It's not that magic. It's just it's a multi-step mechanism. Okay, so ask me in office hours. Say, how do you do the magic step with demurkuration? And I'll tell you. But I can't explain it to everybody without taking a half an hour of time. Okay, so but the basic idea: alkene attacks. You get a mercuronium, which is a kind of secondary carbocation-like. Water attacks that, and now most of the hard work's done, and all you have to do is lose a proton and lose a mercury, and then you have your product, and that's why it's a Markovnikov reaction. Okay. Okay, and continuing our little Chapter 12 mechanistic review. Remember that the anti-Markovnikov reactions, anti-Markovnikov, are a different mechanism. Okay, so for example, if I have the alkene and of course if I do HBr, what happens? HBr, as we just reviewed, would make a Markovnikov, right? The Br would go there. But how do you turn this reaction to anti-Markovnikov? You have to add something. Remember that? You have to add peroxides. And HBr peroxides, or specifically, this is an easy one, is tert-butyl, oxygen-oxygen tert-butyl. That's an example of one of the peroxides you use. And that makes it anti-Markovnikov. Anti-Markovnikov. I'll just abbreviate. It's anti-Markov. Okay, and this is a cool mechanism, and I'm not going to go through it here because we'll learn about the Alkyne version. I'm just going to say a radical mechanism because that's what, we learned it in Chapter 12. I think it was section 12, 13 even. And it was covered in Organic 1. So, but the big thing is this is not a carbocation mechanism. It's not like make a carbocation, which is what happens to make you the Markovnikov product. This is a total anti-Markovnikov product, and yeah, cool. Okay, and what other anti-Markovnikov reactions do you know? Do you know any other anti-Markovnikov reactions? They often correspond to the Markovnikov versions. So this is, the Markovnikov version is just HBr, and it makes the Br Markovnikov. What about like the one that gives you a anti-Markovnikov alcohol? So how do I make an anti-Markovnikov alcohol? Remember that? So let's write that, anti-Markovnikov. Remember, we have those cool review sheets from earlier in the course too that help to remember these reactions. But yeah, well, of course, the Markovnikov alcohol was the mercury one, right? We call it OMDM, Oxymercuration Demurkuration. That makes a Markovnikov. But if we want anti-Markovnikov, it's a two-step reaction. My abbreviation for this one is called HBOX, which is hydroboration oxidation. So it is BH3 is step 1. Step 2 is H2O2 and NaOH, sodium hydroxide. BH3, H2O2, NaOH. So in a nutshell, I'm actually going to I'm not going to review this mechanism because it's a little time intensive, and we already did it in Organic 1. What I will say though, in summary, and you can totally review it, is it's a concerted syn addition which essentially attaches the boron to the end carbon, attaches the boron to the end carbon, and then the boron gets converted to oxygen through the next step. We'll see this again in this Alkyne chapter. I'm not going to review every little bit of chapter 12 though this second. Okay. Okay, so now what's new? For alkynes? Well, it's really cool that alkynes are very analogous. Not totally analogous, but pretty analogous. It's a different kind of double bond. It's a triple bond, right? But the general reactions for alkenes will have some kind of corresponding reaction for alkynes, which is super cool. I'm going to do one immediate example, which is you know how with alkenes, if you do Br2, alkenes with Br2, we call it dibromination. What do you think it's going to be if we have an alkyne and we do Br2? It's going to be tetrabromination. So we're going to brominate 4 times. Okay. So Br2, I'm just going to say excess. And check it out. We get 4 bromines. Br, 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 Br. And this is going to be very analogous to how we did the dibromination of an alkene. So what do you think the mechanism is? So what does the alkyne do to the Br2? Just like an alkene did something to the Br2, this kind of attacks, kicks it off, and now you got another kind of bromonium type intermediate, Br, right? Because you first have the triple bond, and now when you have one of the bonds attack, you're left with a double bond. So this is kind of like a cyclic bromonium, just like we did with alkenes. And then Br attacks again, kind of like this. All right, and now what do you got? Br, Br. Okay, and you have more Br2. What's the more Br2 going to do? Now you're kind of in alkene territory, so it's just an alkene and Br2, and so attack, do it again. This molecule looks pretty weird, but you got a couple Brs, and you also got another bromonium. Isn't that weird? Right? You have the 2 Brs that you installed just a second ago, and you have a third Br, which is bromonium. And now you have some more Br minus, and Br minus is going to do what? It's going to open up something like that, and then what you're left with? A tetrabromo alkane, right? Cool. Okay. Alright, so let's do some more reactions. I think what we're going to do now are, first we're going to do the Markovnikovs, and then we're going to do the anti-Markovnikovs. First, Markovnikov Alkyne reactions. Next, anti-Markovnikov. Sweet, okay. Alright, so let's do these kind of Markovnikov reactions of alkynes first. Markovnikov reactions of alkynes. Then we'll do the anti-Markovnikov ones. So, just like with alkenes, I think one of the first ones to start with would be just like HBr, right? Hydrobromination. Alright, so what we're going to show now this is a little bit weird as we're drawing it, because we're not showing like a clear more like a more substituted side of the alkyne, but what we will show for this Markovnikov hydrobromination is that if we react with HBr, and you'll attach an H and a Br, but the big thing is that the second Br goes where the first Br is, and that's kind of why we're calling it Markovnikov. So the first one isn't really directed, right? It's just, you're going to get an H and a Br assigned to these two carbons, but when the second one comes in, it's going to go where the first one was, and that's why it's called Markovnikov. Okay, and this is also we're gonna say XS meaning excess, and we're also going to give this a name. This is called a gem dihalide or dibromide. Gem in this case means geminal, which means at the same place. Okay. There's two H's also, and those are on the other carbon. But this is the product. The mechanism is incredibly straightforward. What do you think is going to happen? As we're drying it, we're putting the H's on the left carbon, but of course they could go on the right carbon as well. But what is the alkyne going to do to the HBr? It's a nucleophile, it's an electrophile, so what's it going to do? It's going to attack, just like you did in the alkene chapter. And you get this kind of carbocation type thing, right? And it is SP-like, and that's why I draw it kind of linear like that. That's a carbon right there. There's a carbon right there, right? There's not an easy way to show the carbon, but yeah, there's totally a carbon there. Just like there's 4 carbons here. 1, 2, 3, 4. You have 1, 2, 3, 4. Okay. Now what is Br minus going to do to the carbocation? It's going to attack it. It's going to attack the carbocation, right? It might be better if I draw the carbocation on the bottom. No big deal. That looks a little better, right? Alright, so that's cool. H, then we got... Oh, we still have an alkene, right? Okay. And how do we finish this off? Now we have 4 carbons. 1, 2, 3, 4. Well, we do it again. But this is where it's kind of going to be Markovnikov, and I'll explain why. Because in this case, you know, we talked about Markovnikov addition to alkenes last semester. Well, this is now kind of like a tri-substituted alkene, right? So it makes sense that the right side is more substituted, and that's where the Br is going to go. So that's why we're calling it Markovnikov. And just draw another HBr. Okay, and what's going to happen is the alkene attacks. Okay, and what do we have now? I'm going to ignore, well actually, let's draw this. Okay, so now we have, on the left we have 2 H's. And we have that, right? Because the alkene attacked H, displaced off of Br. So now it's the same molecule, but we have an extra H. Br's not there yet, it's not attached. This is the old Br. What do we have now? What was this? Carbocation, right? And it's actually kind of a nice happy carbocation because it's tertiary-like, right? It's like we have 3 things on this carbocation, right? And we know carbocation stability has to do with the amount of things. So this is a happy carbocation, and there's an additional source of happiness. In addition to being tri-substituted at this position, there's actually resonance, which almost always you don't see resonance with normal carbocations that you've seen. But this one actually has resonance because it has a lone pair, right? So there's actually, I can kick in the lone pair and draw a resonance structure, which stabilizes the whole thing. And where's my charge now? Well, the Br donated its lone pair. It has 3 initially, now you have 2 lone pairs, right? If it donated its lone pair, where's the charge? It's on the bromine now, right? So I'm going to actually put brackets around this and say, well, this is actually kind of a stabilized, extra stabilized carbocation, right? I'm even going to go a step further and call it an RSCC. What do you think that stands for? RSCC. It's a carbocation. That's a CC. RS, what does that mean? It's a resonance stabilized carbocation, because there's resonance between the two structures, and resonance stabilizes things. So this thing is semi-stabilized and kind of a happy carbocation. So, all right, and then how do we get to the final product? The gem dihalide, dibromide. How do we get all the way up top there? So now what I'm just going to do is just draw another Br, the other Br minus. And we know that this position is electrophilic, right? The carbon is electrophilic because it's a carbocation. So I'm just going to have it attack right there. And now it's attached, the second Br is attached, and this gives us the product. So I can just draw a big long arrow up to the product, okay? So this is kind of, we call this Markovnikov. We call this reaction Markovnikov because, not because of the first reaction, but more the second reaction. The second reaction installs a Br at the more stabilized, more substituted position. Okay? All right. Now, is it possible to just stop this halfway and just like go to the first point? And the answer is yes. It is possible to only add one HBr. And we will see this again later in the chapter. I just want to mention it. So if we had HBr, I say 1 EQ. What does that mean? 1 EQ. It basically means one molecule this, one molecule that. One molecular equivalent. And you will totally make this. Interestingly, you might get a mixture of stereoisomers. You might get a mixture of E and Z. Remember E and Z from alkenes? It's a stereochemical designation. So you might get this stereoisomer, you might get the other one. Okay, so, but anyway, it is possible to do kind of like a single addition, and we'll see why that's useful later in this chapter. Other stuff, while we're talking about this reaction, this hydrobromination reaction, do you think it'll work for HCl or HI, like different acids? We use HBr, but what about like HCl or HI? And yes, it also works for HCl and like HI. Other have these mineral acids like HCl and HI. Okay. Alright, so we're still on number 8, which was the Markovnikov reactions. Markovnikov. And what other Markovnikov reactions are there? Just like we had for alkenes, we also have a mercury one, Oxymercuration. But for an alkyne, what it was a product of the Markovnikov oxymercuration of an alkene. What was that product? It was an alcohol, right? But with alkynes, the product's a ketone, so it's going to be a different functional group. Now we're learning new ways to make functional groups. Make a ketone, all right? So let's do the basic idea, and then we'll go through the mechanism. The basic idea is that if you have a alkyne And we're using a terminal alkyne in this example, and because you can really see the Markovnikov feature if you do a terminal alkyne. What is Markov? We know what Markovnikov means, right? It means it's more substituted. And anti-Markovnikov is less substituted. What's the other word? Like when we say Markovnikov or anti-Markovnikov, what's the word that that describes what that is? It's called regiochemistry. Regiochemistry, which just kind of means like the region of the molecule. So like if it's an oxymercuration, it's operating and installing the oxygen on the more substituted carbon or more substituted region of the molecule. So Markovnikov is also called kind of like a type of regiochemistry, right? Okay, so I say what the functional group is. How many carbons do we have here? 1, 2, 3. And all right, so there's my 3 carbons. Where's the ketone? Well, what is a ketone? A ketone is a acetyl bond O. It's right there. Totally Markovnikov, right? Because the oxygen's on the more substituted side of this alkyne. Now you might immediately say, well, I know what the reagent is. You think back to your alkene reactions and you're like thinking, I know that mercury acetate does this, right? Mercury acetate. You think, because that's what we learned before. Well, this is one of those kind of frustrating examples where alkynes and alkenes use a slightly different reagent. And that makes this a little hard to learn, but if you have index cards or something, you'll get this. So it's mercury sulfate. It's not mercury acetate, it's mercury sulfate. HgSO4. Okay? That's HgSO4. And acid water. Sometimes the acid water is just sulfuric acid, which is H2SO4. So sometimes in different books, what you'll see is HgSO4, H2SO4, right? HgSO4, H2SO4. But anyways, it's acid water is the reagent. What's the other difference? Because remember in alkenes, it was mercury acetate, HgOAc2, and it was NaBH4, which is a reducing agent. This is not a reducing agent, and so there's a couple differences between the alkene reaction and this alkyne reaction, and one of them is no NaBH4. The other difference, of course, is not mercury acetate, but mercury sulfate. And you get a ketone out. Okay, so what's the mechanism of this? And yeah, we'll step through the mechanism of this reaction. Okay, so let's do the mechanism of the oxymercuration of alkynes to give ketones. So the mechanism. So what I'm going to do is I'm going to kind of redraw it a little bit. Draw the product. So I'm also going to redraw the sulfate in a manner that I think really helps in the mechanism. So of course, mercury sulfate is Hg2+, so I'm going to draw Hg2+. Cool so far? Hg2+, right? And that means there's a positive 2 charge, and that means on the sulfate there's a negative 2 charge, right? So I'm going to draw kind of O, just like a negative and negative, right? And the sulfur. Okay, and the sulfur, of course, is here. I'm giving him different colors. It'll help maybe a bit. So that's what HgSO4 is, right? Hg2+, SO4, 2-, right? All right, so there's our reagent. It's a good start. We also have H3O+, acid water. So what is the alkyne going to do to this crazy molecule? What's the alkyne going to do to this? Well, just like what did in the alkene reactions, the alkyne kind of attacks the mercury, right? So sort of like this. Okay? And that sort of breaks off one of these. Okay? And what does that look like now? What do we got? Well, we got the alkyne thing that's not an alkyne anymore, it's more of an alkene type thing, right? And we have the H down here. And remember bromoniums, and what's the analogous thing to a mercury style bromonium? It's called Mercuronium, right? And so this is kind of like now, and I'm using dotted lines because the bonding is not exactly clear, but it's mercury bound to both carbons, and we have an SO3 minus, and the charge is now positive on mercury. So what are we going to call this thing? Well, it's also a Mercuronium-like species. Mercuronium ion, right? And just like we saw before with the alkenes and reviewing all this, it kind of acts like what sort of carbocation? It kind of acts like a carbocation on the internal position, not on the terminal position, but on the internal. So it kind of acts like a secondary carbocation. And by secondary carbocation, I mean the internal position. Alright, so that's cool. And now, I'm just going to go downward. We got a couple little steps to draw. We draw H2O, and what's H2O going to do to this thing that looks and acts like a secondary carbocation? So the water is going to attack the secondary position. Alright, and that kind of breaks off the mercury. And what do we get? I just call this now HGX. It's just Hg with some junk on it. And we have a OH2 plus, right? Alright. And now I'm going, this is an extra proton and oxygen, right? I'm just going to assume it comes off, minus H plus. If I want to draw a mechanism for it, it's really easy. I would just draw water. You know, more water takes the proton off. The big thing though is it loses a proton, right? Alright, so we are X on Hg still. Now you have OH. Okay, see where we are? Now, just kind of like we kind of punted on this in the alkene chapter, I'm going to just say minus HGX. Minus HGX. A procedure happens where the mercury gets lost. And this involves the water, because we have a lot of water around, right? But the net effect is it goes away. You could call this magic if you like. Okay, we cool? If you want to ask about this, I'm happy to talk to you about how it loses the mercury, but it's not something you care about. We're kind of focusing on the major parts of this mechanism. Okay, so now we're pretty much at the end of the mechanism. This thing is kind of like an alkene with an alcohol, right? See how it's kind of an alkene with an alcohol? We're going to give this a name called Enol. Enol. It's like a half ene, half alcohol, right? Enol, right? And a reaction occurs that we'll address it later in this course, but we're not quite there yet, where the enol can rapidly equilibrate to this form. And of course, what functional group is this? It's a ketone, right? That's a ketone. Well, anyway, this is called an enol tautomer, tautomer, T-A-U-T-O-M-E-R, tautomer, enol tautomer. And this will equilibrate to this thing called a keto tautomer. Keto, K-E-T-O, tautomer. It's a rapid equilibrium. It's a very simple mechanism. We just teach it in a couple chapters. But for now, for you, you can just assume, oh, if I see an enol, it just rapidly equilibrates. The enol rapidly equilibrates to the keto form, which is and they're called tautomers. That's a tautomer, that's a tautomer. What do you think the equilibrium is called? It's a tautomerism. I'll try to draw it a little down there. Tautomerism. That's the name of the equilibrium. Tautomerism. Tautomerism is the name of this equilibrium. It's called, and it's keto-enol tautomerism, and it's actually a very simple mechanism, but we just don't explain it until a couple chapters from now. Yeah. Anyway, that is the overall process. Definitely, if you have index cards, I would copy this all down. The alkyne attacks mercury sulfate. That's pretty straightforward. You make a mercuronium. It acts like a carbocation. Water attacks the secondary position. Still got an extra proton. Lose the proton, and now you have a alcohol. Demurkurate. Don't worry about the mechanism. Say magic if you like. And then now we're in this tautomerism world where the enol tautomer tautomerizes, or it's a tautomerism reaction to the keto tautomer, and then you are done. And that is the oxymercuration of alkynes, which is a Markovnikov reaction. Alright, so another thing about this tautomerism concept, tautomerism, between the enol and the keto tautomer. This is a preview of some stuff we'll learn later. It's really not that bad though. Typically, for all types of acetyl bond O functional groups, ketones, aldehydes, also esters and other things, we'll learn about this in chapter 18, is if you got like a ketone or aldehyde, they have these two forms. Right? And what do we call them? That's okay. Enol, right? Enol tautomer. And a keto tautomer. And they are in equilibrium. So it's really right-sided favored equilibrium. That equilibrium has a name. It's called tautomerism. Tautomerism. And the mechanism is actually really straightforward. Mechanism is later though. We're going to talk about it in chapter 18. It is easy though. It's really just the movement of a proton, right? There's a CH2 there and a CH there, right? So basically what you can see that we're moving the oxygen, the OH, from the OH to the next door carbon. So it's like a transfer of a proton from the oxygen to the position next to the ketone, right? So it's just a movement of a proton. That's what tautomerism is. Okay? All right. Let's do a quickie synthesis using this new reaction, the Oxymercuration reaction. Synthesis example. Just to massage it into our brains a little bit. Actually, well, this is Not even a synthesis example, just a reaction example. So if I have like benzene with 2 alkynes, and what's the reagent to do the mercuration? Let's draw the product. So both alkynes are converted to ketones, which are Markovnikov, right? Is it mercury acetate and NaBH4, or is it something else? It's mercury sulfate, HgSO4, H3O+. And we're assuming kind of excess, so both functional groups react. Okay, cool. Alright. Let's do a synthesis example now. Synthesis example. What if we have a ketone and we're like trying to convert it to question mark synthesis, multi-step synthesis to an alcohol with a ketone like that. And you immediately might say, wait a minute, I don't see any alkynes here. Are we in the alkyne chapter, right? But you do see that ketone, and you're like, well, I just learned how to make a ketone. I mean, I know how to make ketones from alkynes. So you could say that this this ketone might maybe came from alkyne, right? Maybe came from alkyne. Because ketones can be created from alkynes really easily. And so maybe we'll just go backwards while we're thinking. And all the other thing, of course, is this, right? Squiggly. That's the other thing, right? So you're clearly connecting a 2-carbon piece, right? So maybe from acetone, you're attaching a 2-carbon piece, maybe an alkyne 2-carbon piece, right? Because we know that alkynes attack ketones. And then once you got the alkyne, you just turn the alkyne to a ketone, right? So maybe, going backwards, make it from an alkyne. And this is really easy. We know how to attach alkynes to ketones. What are the reagents for the transformation of an alkyne to a ketone? HgSO4, H3O+. Okay. And how do we attach a 2-carbon alkyne type piece to a ketone? Well, you know, you can, of course, you need a nucleophilic alkyne, right? It needs to be a nucleophilic alkyne. In this situation, we're just going to assume it's already like pre-deprotonated, like an alkynyl anion, 2-carbon alkynyl anion, because we know that this is a nucleophile, and this will just attack. And what's the second step? To provide a proton on the alcohol, right? We don't need a mechanism, but if we want, you know, if it's a simple arrow, it doesn't hurt. This is not a mechanism problem, but that is what the mechanism is. I don't necessarily recommend you drawing mechanism arrows for every synthesis problem, but if it helps you, you know, to remind yourself, that's okay. It's just not necessary. I never really require mechanism arrows on synthesis problems. Okay, so yeah, this attacks, then you get an O-, and then that tells you what step 2 is going to be. What does the O- do to get turned into an alcohol? Maybe water or something. So yeah, that was a pretty easy synthesis problem. Okay, cool. Alright, I'm going to just introduce the next reaction. I'm going to stop. So next reaction, well, the next topic is anti-Markovnikov addition. Anti-Markovnikov addition to alkynes. Alright, that means that you're adding stuff to the terminal position of an alkyne, as opposed to, like in this case, we're adding the oxygen to the internal position. This will add stuff to the terminal position, like the very end, right? Okay, so I'm just going to introduce the first one, and then we'll talk about it next time. So radical addition of HBr. Radical addition of HBr, hydrobromic acid. Okay. So let's just show an alkyne. And remember, how do we do radical addition of HBr? It wasn't just HBr and radicals, it was HBr and a specific kind of reagent. HBr and something like a peroxide. Tributyl peroxide, or we'll say peroxides. Okay? And what that does is it'll attach Br to the very end. Okay, and that's what we mean by anti-Markovnikov. Alright, so now it turns out when we do this, how many carbons is this? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There are two products, like two stereoisomers. There's like trans, and you might make cis also. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so that issue is not a big deal. I'm just saying, oh yeah, there's two stereoisomers. But it is anti-Markovnikov. Just write that down. Anti-Markovnikov. Okay. The mechanism we'll do next time. So it's a radical mechanism. And if you remember the radical mechanism for alkenes, of how this works, because the same reaction occurs for alkenes to do anti-Markovnikov hydrobromination, it's the same exact mechanism. So, but for now we're just going to stop, and we'll deal with that next time. Cool. If you want to read about it in the book too, it's pretty straightforward. We're doing pretty good. I think next time we're going to finish these reactions and jump into the next chapter. Alright, see ya.